Good day, sir. I'm Vonn Mirabueno. I'll be presenting my research on operating systems in edge computing. This study involves meeting the specific requirements for operating systems in edge computing environments, ensuring low latency and high reliability. And these are the contents that will be discussed later on. First, we have introduction. For the background, edge computing processes data closer to the source to reduce latency. Because what makes edge computing interesting is how it reduces delay by working with data right at the edge. That's a huge advantage for over relying on distant cloud servers. It's the reasons we can have real-time systems like smart traffic control or wearable health devices. And for the research problem, I saw that traditional operating systems can't meet the needs of edge computing. Because as I look deeper, I saw that many current OS architectures are just too bulky or complex. They weren't made for small, distributed devices. That mismatch is what pushed me to explore this topic. And for my objectives, I have one objective to identify the key OS features needed in edge environments. My goal was to understand what OS features are most effective in edge computing. I wanted to figure out what actually works, not just in theory, but in practice. This helped me shape my analysis around real challenges. For my significance of the study, it helps to improve real-time systems in fields like IoT, automation, and healthcare. I believe this research is important because so many industries now depend on edge computing. From industrial machines to smart homes, it's everywhere. A strong OS can make a big difference in reliability and speed. And for my scope and limitation, I focus on OS architecture, excluded hardware design, and up-level software. To stay focused, I limited my study to the software side, specifically the operating system layer. I didn't dive into hardware specs or specific applications. Just let me go deeper into OS design principles. Next, literature review. For overview of my research, I saw that traditional OS models struggle in edge scenarios. Many earlier systems were designed for desktop or cloud servers, not edge devices. I found that monolithic OS kernels are often too heavy for limited environments. That's why newer systems are exploring different architectures. For my theoretical framework, microkernel and container-based architectures provide flexibility. This is because microkernel focus on only essential functions which make them easier to manage. Con- Containers allows apps to run in isolated environment, so updates and failure don't crash the whole system. I found that both approaches were effective for edge setups. For my research gap, I noticed that it lack of unified standards and real-time adaptability across devices. Even with all this progress, there's still no consistent standard across edge platforms. Devices vary too much, and systems often don't work well together. This gap really stood out as an opportunity for future work. For my methodology, my research design was qualitative approach. I chose a qualitative design because I wanted to focus more on understanding ideas than measuring numbers. It gave me room to analyze case studies and expert perspectives. That approach made the most sense for this topic. For the data collection, I reviewed academic studies, tech, technical documentation, and case studies. I gathered all information from both scholarly journals and actual systems like Velotalk, EgoOS. Seeing how these systems work in the real world helped a lot. It made the theory come alive. And for the tools and technologies, I analyzed OS like Velotalk, EgoOS, and Chalmers Edge OS projects. This is because their system had a clear patterns, lightweight, flexible, and secure. I noticed that companies and researchers are starting to adopt these designs more often. They seem to work well under edge conditions. For analysis, I identified recurring architectural elements that support edge demands. This is because my main task was to spot what these systems had in common. The more I compared them, the clearer it became that some features kept showing up. That consistency helped shape my recommendation. And for the result and discussions, I had three findings. The first finding was microkernel based OS are ideal for edge devices because of their small size and modular structure. This is because I found that microkernels keep the OS light and flexible, which is exactly what edge devices need. They run only what's necessary, that makes them more stable and easier to maintain. Next, I have finding 2. Containers provide safer and easier app deployment. This is because containers separate application from the core system. If something goes wrong, it doesn't crush everything else. That kind of stability is really valuable in distributed environments. And lastly, for finding 3, AB update system enhance system reliability by providing backup OS versions during updates. AB updates systems give you a backup version of the OS in case the new one fails. That's especially useful when devices are remote or hard to access. It's a smart way to prevent total failure. This finding these findings it aligns with previous work such as those by Enberg, Suen Lee, and Roman et al. It was encouraging to see that my findings aligned with other researchers. Their work confirmed the value of modular OS design and secure update systems. It added more confidence to my conclusions. And I saw that one of the challenges on this research was standardization across different edge setups remains an unsolved problem. Even with good tools, edge computing still lacks a consistent way to handle interoperability. That surprised me the most. It's something the industry really needs to work on. And this is the summary of my key findings. This graph illustrates the key operating systems features essential for edge computing environments. As you can see, it's ranked by their importance at the top. We see modular and microkernel design and security features both scoring high due to their role in maintaining lightweight, flexible, and secure operation, to be followed by containerization and distributed OS architectures. Also rank strongly as they enhance scalability and simplify deployment across edge nodes. Next is real-time research management is moderately important, especially where responsiveness is critical. Interoperability remains a challenge, but it's crucial for ensuring compatibility across diverse hardware. And finally, we emphasize the importance of designing future-ready OSs, ones that are adaptive and can handle evolving edge workloads. And lastly, for the conclusion and recommendations, for the summary, I noticed that modular OS, containers, and secure update methods are essential for successful edge computing. This is because these three qualities kept showing up in every successful system. Without them, the OS either slow down or becomes unreliable. They form the core of any strong edge design. And for the implication, the right OS can make edge computing faster, safer, and more scalable. What I realized is that the OS can either support the systems or hold it back. A well-designed OS can make real-time systems much faster, more efficient, and safer. It's a critical part of edge success. And for the applications, the research is applicable in fields like smart cities, autonomous systems, and industrial automation. This is because this isn't just a theory. It's already being used in traffic control, robotics, and factory machines. These systems rely on fast, secure, and flexible OS. That's why this research feels so relevant today. And for the future work, research should focus on interoperability and adaptive OS frameworks. I believe that the next step is building smarter OS frameworks that can adjust on their own. We also need consistent protocols so different devices can work together. That's the direction I think the future research should go. And, and that's it. Thank you.